Hi everyone, in this lesson we're going to look at confidence intervals for a population mean. You might want to pause the video and read the problem and then we'll work it out together. A Toyota Prius, a hybrid car, is advertised to get 50 miles per gallon. Harold has a Prius and he wonders if his car gets that advertised mileage. He keeps records of his mileage for 20 tanks of gas. The mean mileage of the 20 tanks was 48.5 miles per gallon, and the standard deviation was 2.4 miles per gallon. Consider the 20 tanks to be a random sample of all the tanks of gas for Harold's Prius. The first thing we want to do is write a sentence defining the symbol mu for this problem. Okay, and mu, remember, is a population parameter. Since we're dealing with the population, and in this case it's the mean, it would be the mean mileage for all Toyota Prius. And it's important to use the word all because all signifies the population. And remember that we don't know mu. Mu is unknown, which is why we're trying to find a confidence interval. So our goal is to be able to take a random sample and to be able to create an interval that contains the true mean gas mileage for all Toyota Prius. So we're going to make a 95% confidence interval for the mean gas mileage. And essentially what that means is if, let's say, I took 100 random samples, approximately 95% of them would capture the true mean gas mileage for all Toyota Prius. So if you'll remember, my formula for confidence intervals is the point estimate, which in this case is my sample mean, plus or minus the margin of error. And the margin of error is constructed using your critical t-value. And the reason we're using t is because we're dealing with means, and we're using a t-model, which is the normal model that's been adjusted because of degrees of freedom. And then we're going to multiply by the standard error. And the standard error is sigma over the square root of n, but we also don't know sigma. So we're going to take the sample standard deviation and divide that by the square root of n. So now I go back to the problem and I can see that my sample mean, x bar, is 48.5. And then plus or minus my critical value. So my critical value is determined based on the degrees of freedom. So my degrees of freedom is my sample size minus 1. And my sample size is 20. And 20 minus 1 is 19. So what I'm looking for then is the t-value for 19 degrees of freedom. And we'll find that here in a second. Then I'm going to multiply by the sample standard deviation, which is 2.4, and I'm dividing by the square root of the sample size, which is 20. So I'm going to open up the t-table to find my t critical value. So the first thing I need to do is make sure I'm in the correct column. Since we're dealing with a 95% confidence interval, we're in the right column. And what I want to do then is find the degrees of freedom on the left-hand side, which will be 19, and go across. And where the two colors meet is my critical value. So it's 2.093. Remember when we were dealing with proportions, if we were creating a 95% confidence interval, you could use the number 2 for your critical z value, but we can't do that because our normal model has been adjusted using the degrees of freedom here. So I need to use 2.093. You can also get that from your calculator. So what you could do is take 100% minus your confidence percent, so 95, and then that means that there's 5% on either side of the model. So I need to divide 5 by 2, and I get 2.5. So that's 2.5% or 0.025. So I need to do the inverse t. So I would hit second vars, And then you're going to pick number 4. And it's saying, what's the area? If you put 0.025, it's going to give you a negative because it thinks it's the lower 2.5%. So instead, you could use 97.5% or 0.975. And then the degrees of freedom, so I need to put a comma, and my degrees of freedom, remember, are 19. And then hit enter, and you're going to get the same exact value that we find on the t-table, which is 2.093. Okay, so we're going to go back now, and we're going to fill in that value. So I have 48.5 plus or minus 2.093, and then my standard error, if I divide 2.4 divided by the square root of 20, I get 0.5367. And then we know that this is our margin of error. So I'm going to calculate the margin of error now. So I would have 48.5 plus or minus whatever 2.093 times 0.5367 is. And it's 1.1233. That's my margin of error. So now I'm going to do 48.5 minus the margin of error and 48.5 plus the margin of error. So when I do 48.5 minus 1.233, I get 47.27, and then 48.5 plus 1.1233, I get 49.62. So I have my interval now, 47, it was 47.27. And then I had 49.62, I believe. Yes. Now, how do I interpret that interval? I would say we are 95% confident that the mean mileage for all, okay, remember we're trying to find the population mean for all Toyota Prius cars is between 47.27 miles per gallon and 49.62 miles per gallon. So Harold's Prius is getting 48.5 miles per gallon, which is within that interval. So the difference is not very important there because they're advertising 50 miles per gallon, which is not really in the interval. If you round up to the nearest whole number, it is. But Harold's miles per gallon is within that interval. So he's not really getting a major lower difference in gas mileage than was advertised. Okay, it is lower, but it's not, the difference is not very important. Okay. That's it for this section, the only thing that I want to draw attention to is you still have to check your conditions. So we make two assumptions. One of them is the independence assumption, and we check that using these two conditions, the randomization condition and the 10% condition, which you're familiar with from hypothesis testing in chapter 2. And the only condition that's different is the nearly normal condition. If you'll recall from chapter 2, when we were dealing with proportions, we did success failure. And we did that using n times p and n times 1 minus p. But we don't have p, right? We have mu. So we can't do that. So instead, we look at the sample size, and when it's less than 15, the data should follow a normal model pretty closely. Unless there's some outliers or strong skewness, then you won't want to use the t-distribution. When the sample size is between 15 and 30, which was our case, the data needs to be unimodal and fairly symmetric. You could check this using a histogram or a normal probability plot, as I showed in class. But we don't have any data here, so we just need to assume that it is a normal model. And when the sample size is more than 30, the t-distribution is pretty safe to use, unless there's extreme skewness, as in when your sample size is less than 15. So really, it's this middle one that you need to watch out for, and you need to look to make sure there's no strong outliers or extreme skewness in your distribution. Please make sure you take the time to look at the summary and also take the time to do the homework and practice. And if you have any questions, please feel free to reach out.